Good morning, students. Let's discuss the space complexity of algorithms. Here, we will be computing the extra memory required with respect to the input n. For any given algorithm, there is a trade-off between time and space complexity. As we all know, algorithms can be classified into iterative and recursive algorithms. Let's consider the space complexity of iterative algorithms. So given a code snippet, here there is an algorithm, right? Here we can see that in this algorithm, array A is the input of size n. Now there are some temporary variables, okay, variable I, and here this code snippet creates a temporary array B of n, okay, that is second array of size n units. Okay, now what is the space complexity of this code snippet? Here, since we are more interested in extra memory required, the extra memory required is n units for this array B and 1 unit for the temporary variable I. In effect, it is n plus 1 units, hence S of n is equal to big O of n. Let's consider the second example. Okay, so here in this code snippet, you can see that we are trying to initialize the elements of this array A with value 0. For the same purpose, we does not require any extra space except for the variable I, which is 1 unit. So S of n is equal to big O of 1. The third example, here we have a nested for loop, and our objective is to initialize a 2-dimensional array of size n by n. Okay, so the extra space associated with this code snippet is n square with respect to the 2-dimensional array, 1 unit for the temporary variable I and another 1 unit for the temporary variable j. Hence, the total sums up to n square plus 2 units. So we can write S of n as big O of n square. Now, let us discuss the space complexity of recursive algorithms. Here a code snippet is given to us. This code snippet, okay, here in this case you can see that we are recursively calling this function a of n with a value n minus 1. Now there are two methods which you can use for computing the space complexity with respect to the size of the program. If the program size is small, we can draw the recursive tree and reduce it. If it is too large, then we have to depend upon the stack method. So now let us discuss with respect to the recursive tree, and wherever required we will be using the stack method to make the assumptions more clear. Let us assume that the value of n is equal to 3. When the value of n is equal to 3, a of 3 is going to invoke a of 2 and printf with a value of 3. Now this recursive call will continue till the value of a is equal to 0. Okay, now here we are going to now scan the tree to understand the space required for each of these calls. Now when the value of n is equal to 3, here we can see that there are 4 recursive calls. When the value of n is equal to 2, it is 3 recursive calls, a of 2, a of 1 and a of 0. Likewise, when the value of n is equal to 1, the number of recursive calls is equal to 2. In effect, we can write it as follows. We can sum up our findings as follows. That is, n is equal to 3, number of recursive calls is equal to 4, so on and so forth. That is, when the value of n is equal to n, the number of recursive calls is equal to n plus 1 calls. Okay. Now let us traverse this tree from top down from left to right and observe what happens to the stack. Okay, now here we assume that every stack entry occupies k units. Okay, every stack entry occupies k units. And since the value of n is equal to 3, number of recursive calls is equal to 4. Okay, that is a of 3, which in turn calls a of 2, which calls a of 1 and a of 0. Each of them is going to occupy k units. Okay, now here we are going to just check whether any extra space is required in the stack. Okay, for the same, we assume that if the node is a function call and the function is unvisited, and that is the function is not expanded, then we are going to perform a push action. If the node is an instruction, we will execute it, and if the node is visited, then we are going to perform the pop action. Okay, now a of 3. So okay, when a of 3 comes, what we are going to do? We are going to push a of 2 onto the stack, and then we will further expand this a of 2, which in turn calls a of 1. So we pushed it onto the stack. Then a of 1 is invoking a of 0, so we are again pushing onto the stack. Alright, now when we are returning back, okay, that means once we have completed visiting this node a of 0, okay, what we are going to do is we are going to pop it off. Alright, and then we will proceed further, and we find there is a statement to be executed. We will execute by printing the 1 onto the screen. Then we proceed further. We are going to visit a node which is a function call which is already been visited. So what happens? We are going to pop off a of 1. Then we print 2. Okay, then we print the 2. Then again we are back onto the node a of 2, which is a function call which has been visited. So what we are going to do, we are popping it off from the top of the stack. Then further when we proceed, we will print 3 and then back to a of 3 which is visited. So we will pop off a of 3. So here you can see the space complexity is dependent upon the depth or height of the stack, that is n plus 1 times k. Okay, now k is the yes, so here in this case k is the memory required for storing each of these recursive calls, which is clear to us. Okay, here we can write it as big O of S of n is equal to big O of n times k, which is equivalent to big O of n. Since k is a constant value here, k is a constant value, okay, we can write it as big O of n. Let's continue with another example. Here we have a recursive function with two function invocation to the same function with the value n is equal to 1. Now, as we have discussed earlier, we are going to again construct a recursive tree a of 3, which in turn calls a of 2, then print of 3 and a of 2. Okay, so here what we are going to do further is, our main objective is to compute the space complexity, right? So here from this it's very clear that when the value of n is equal to 3, the number of recursive calls is equal to 15. When it is equal to 2, the number of recursive calls is equal to 7, so on and so forth. We can write when the value of n is equal to n, the number of recursive calls is equal to 2 raised to n plus 1 minus 1. Okay, so here compared to the previous one, here you can note that the space complexity may not depend upon the number of calls. For that we will have to closely examine the stack. Okay, so we are going to start traversing this recursive tree from top to bottom and left to right. Okay, so here we started from the root node a of 3. So we pushed it onto the stack, which in turn calls a of 2, which in turn calls a of 1, and which in turn calls a of 0. Now, when we have done with visiting this visiting this node a of 0, and when we are proceeding further, that means it is visited, so we are going to pop it off. That is the first pop operation. After that, we have a printf statement, so we printed the value 1 onto the screen. Then next is again a function call. Okay, which is a of 0. So we push it back onto the stack. Okay, we push it onto the stack, and once we completed visiting this node, we are going to pop it off. So this is the second pop operation. Then we are in a of 1. So here top of the stack a of 1. So here after completing visiting all the children of this a of 1, now it is time for us to proceed further to this parent. Okay, so a of 1 is been popped off. So this is my third pop off. After that I have a printf statement to print 2. So I printed 2. Proceeding further, Okay, now there is one more child in A of 2 which needs to be visited, that is A of 1. So here, after 2 pop operations, okay, in total summing up to 3 in effect. So we are moving on to pushing. Okay, we are going to expand this A of 1. So for expanding A of 1, first we'll push A of 1 into the top of the stack and then A of 0. Okay, so A of 0 is pushed. After visiting this A of 0, okay, that means the 4th pop operation, we are going to print the value of 1. Okay, so on and so forth. We visited A of, then we are here to visit A of 1. Okay, and this function call is already been addressed. So we are proceeding further. Okay, to complete this A of 1, we again have to visit A of 0. Okay, so the 5th pop operation. Okay, we are here now. When we are about to leave A of 1, we have to pop it off from the top of the stack. Alright, so when we pop off, now we are in A of 2. So after visiting, so here this tree, subtree associated with A of 2 is already been is completely been explored. So we are proceeding further. So we are going to pop it off from the top of the stack and then we print the value 3. Similarly, the rightmost subtree with a root as A of 2 will be again further explored. So you can see what happens further. Okay, so further we will visit A of 2. Okay, so for visiting A of 2, we will again further explore all the subtrees. Okay, so in effect, once we have done with the complete traversal, okay, we are here with 15 pop operations has been completed. Okay, and the following pattern will be printed. So here, what is the space complexity? Space complexity here does not depend upon the number of calls. Here, when we closely examine the stack, okay, the maximum extra stack space required is equal to 4 n plus 1 times k. That is, if the value of n is equal to 3, that means I require only 4 entries into the stack, each of size k units. Hence, the space complexity here is n plus 1 times k, which is big O of n.